Today, I think we're going to cover 3 sections today. 3.1, 3.2, and 3.3. And they're all related. So I'm going to, instead of breaking it down into individual sections, we're just going to teach all of them at one time. How about? I can do it. I know I can. I'm going to start on page 158, in case you need to know that. Page 158. And these 3 sections together, they're on solving systems of linear equations. Solving systems of linear equations. And if I break that down to help you understand what that title means, first of all, systems. When you see the word systems in math, it means more than one of something. Systems means multiple, okay? Linear equations means equations that when you graph them, you get a line. And can y'all imagine if I have more than one line on a graph, what do they normally do? Intersect, okay? So when you're solving a system of linear equations, basically that boils down to finding the point of intersection. We're looking for where do these 2 lines cross. And so that means hopefully you can imagine the answers are going to be ordered pairs, right? If I'm finding a point of intersection, then I'm finding ordered pairs. So on page 158, we're going to start with problem number 1. And here's what the instructions say. It says solve each system of equations graphically. Graphically means I'm going to need to sketch the graph of each one of those and then locate the point where they cross. From the picture, right? Okay. And then it says classify the system as consistent or inconsistent and dependent or independent. And so you're going to need to know what those terms mean. So far, so good? So I'm going to graph these lines, and we're going to see if we can tell where they cross. Now, are these equations in slope-intercept form? In other words, do they have y by themselves? And so I'm going to use what's called the intercepts method of graphing, because if it's not in slope-intercept form, then the intercepts method is easiest. Did y'all make a note of that? We're going to use the intercepts method of graphing. All right, so for the first equation, I'm going to let x be 0, and then I'm going to find what y is. If I let x be 0, the x disappears, and y is 4. And do y'all see that that gives me the y-intercept? 0, 4 is the y-intercept. And then I'm going to let x be 0. Oh, did I just say x? I'm sorry. I'm going to let y be 0. And if I let y be 0, the y disappears. X is 4. And that is the x-intercept. Now, do y'all see why that is called the intercepts method? Because it gets me the x-intercept and the y-intercept. How many points does it take to graph a line? I've got them, but let's plot them. 1, 2, 3, 4. 1, 2, 3, 4. All right, so there is the first equation graphed using the intercepts method. And now what I'm going to do is I'm going to graph the second equation using the intercepts method again. All right, here we go. X and Y. And we're going to let X be 0 one time. If I let X be 0, the X disappears. And then notice this one's going to have a little bit of work to get Y by itself. So if negative Y equals 2, what does positive Y equal? Negative 2. Did y'all catch that? I can do it again if you need to see it. Instant replay in slow motion. Okay, if X is 0, the X disappears, and I would need to move the negative to the other side to get Y by itself. So moving that over makes that negative 2. Got it? And then I'm going to let Y be 0. So if I let Y be 0, the Y disappears. X is 2. Again, using the intercepts method. You let X be 0, you let Y be 0. How many points does it take to make a line? 2. I've got them. Let's plot them. 0, negative 2, 2, 0. And I hope y'all can tell that you're going to have to be pretty accurate with your graph to get that point of intersection. Right? You can't be quick and, what is it? You can't do it quick and, I don't know what I'm trying to say. You can't do it quickly and not accurate. It's got to be really accurate to get the point of intersection. All right, so there's where they intersect. Can you tell me what that point is as an ordered pair? 3, 1. Now, I think they intersect at 3, 1, okay, based on my picture. But what I'd like to do is I'd like to test and see if that's correct. So if this is really the answer, when I substitute it in for both equations, should it work out? Should it give equality? Yeah. And so we're going to plug this into the first equation. 3 plus 1 equals 4. Is that true? Okay. And then we're going to plug it into the second equation. 3 minus 1 equals 2. And is that true? And if they both work out, then you verify that that is the point of intersection. Everybody see that? Now, I got to tell you, solving by graphing is my least favorite technique, because if that ordered pair is not a nice integer number, like if it was 1/3 and negative 7/3 or something, you're not going to get that from a graph. So graphing is useful, but it's not going to work really nice every time. You understand what I'm saying? Okay. And since we're talking about graphing, it wouldn't be right to not talk about Desmos, okay? So let's look at how Desmos does the same thing for us. X plus Y equals, what was the first one?
4.
And X minus Y equals? 2. And Desmos is so freaking easy. You just type it in and you click on the intersection. I don't know. Did y'all see how quick and easy that was? You put in your 2 equations, you click where they cross, you've got your ordered pair. So easy. I love Desmos. Man, does anybody have any questions so far? Anybody? Okay, next problem. Let's do number 1. Yeah, we're doing Britney Spears, okay? Oops, I did it again. I did the same problem and got the same answer. Oh, baby, baby. Let's see here. Give me 1 second as I finalize my roster. Oh, there's another one. All right. Number 1. So how did we solve number 1 first? Graphically, right? We used a graph to find the intersection. Now what we're going to do is we're going to solve this using a technique called the addition method. Y'all might want to make a note in your notes. This is going to be the addition method. And the addition method is good if you can add the equations together and get a letter to cancel. Did y'all catch that? Addition method is good if adding the equations together gets one of the letters to cancel. So if I add those together, which letter will cancel? Y. And so we're going to use the addition method, which pretty much does what it says. You're going to add x plus x. There you go. Plus y minus y. Cancel. 4 plus 2. 6. Do y'all see that? Adding together gets the y's to cancel. And now look, I can solve for x. Divide both sides by 2. X equals 3. And notice that that does verify my x coordinate of the intersection. Now, if I know x, I also need y. And that means I need to plug this back in to either one of the equations. You don't have to do both. So which do y'all prefer, top or bottom? Do you want to plug into the top equation or the bottom equation? I'm going to have to go with top this time. So if I plug that 3 back in, it's going to say 3 plus y equals 4. And so 3 plus what equals 4. And then that tells me that y is 1. 3 plus 1 is 4. And then I can write that as an ordered pair, x comma y, 3 comma 1. And do y'all see I get the same answer with a different technique?
But are you always going to be able to use that technique, or are you going to have to use that one too?
You can always make addition work. You can always make the addition method work, okay? You can always use Desmos to graph. If you have Desmos handy, it's pretty easy to download the app to your phone, right? I can just imagine y'all shopping at Walmart and using Desmos to figure out what type of peanut butter to buy or something. Yeah. Or like, I'm going this way and my wife's going this way, and I know we're going to meet, in the frozen section or something where the lines intersect. Never mind. All right, so there is a third technique. There's graphing, there's the addition method, there is a third technique. Do you want me to rework this again, or do you want to go to a new problem? And you want a new one? Okay. Number 7. And I'm still on page 158. Now, do y'all notice that this set of equations is actually started as a function? Did y'all see the function notation? So I guess the first thing we might want to do is, how can I tell that those are linear? What is it about those that tell me it's a line? Oh, okay, so there's only the x, but what does f of x represent? And so there's actually two variables. There's an x and a y. And it's something about these x's that tells me they're going to be lines. Good. She beat you by a fraction of a second, didn't she? Yeah. There's no exponents. Y'all see that? X to the 1, they don't have squares or cubes. So that means these are going to be lines. I know they're linear, right? And can I replace f of x and g of x with y? So what I'm asking is, can I say y equals x minus 1 and y equals negative 2x plus 5? Can I do that? Same thing, right? So these mean the same as these, written with y. And the third technique that I would like to teach you is called the substitution method. Substitution. Okay? So for the first equation, do you see that y equals x minus 1? And that means anytime I see a y, I can replace it with x minus 1 because y equals x minus 1. Y'all understand what I just said? So look, I see a y right here. So I can replace that with x minus 1. So what did I just do? I substituted for this y what it's equal to. And now I've got a single equation with only x. I can now solve for x. So we're going to move the minus 2x over, and we're going to bring the minus 1 back. And that's going to give me 2x plus x, 1 plus 5. And divide both sides by? So that's the substitution method. I replace y in this case with what it's equal to, which allows me to solve for x. And am I done, or do I still have stuff to do? I got to get y, right? So if I know x, I can bring that all the way back up here, and I can either plug into this x. Are y'all looking at what I'm pointing at? I can plug into this x or this x. Either one of these will calculate y. So you want to go top again? Okay, so we'll bring it all the way up here. And that says y equals 2 minus 1. And then I need to write that as an ordered pair. You always need to write it as an ordered pair. And what technique was that? Substitution. That was the substitution method, okay? And guess what we're going to do to verify that? I'm going to go back to these original functions, and I'm going to graph them. Just for fun. This is just for fun now, okay? Just to see if the graph verifies what I did algebraically. I want a visual representation of what I did algebraically, okay? Now, the reason I'm going to go back and graph these is because they are in slope-intercept form. Did y'all notice that? They have the y by itself. And I can do the graphing poem. The plot the B, rise and run, connect the dots, then you're done. Have y'all heard that from me before? So for the first line, I've got -1 is the y-intercept, and the slope is 1. So I'm going to rise 1, I'm going to run 1 from -1. And I'm going to get a line going through like that. That's my first line. My second line has a y-intercept of 5. So I'm going to go way up to 5. And then what is his slope? And so that's going to be rise over run, negative 2 over 1, which means I'm going to go down 2 and over 1. And I'm going to get a line coming through like that. Now you tell me, does it look like those lines intersect at the point 2, 1? Over 2, up 1, pretty close, right? So the graph can help me visualize that the point really is 2, 1 where they intersect, okay? Do I need to use more than one technique at a time? Need. Sometimes you may want to, because you're like, I like doing all the math, right? I want to do it 3 different ways just because I enjoy doing math so much. No? Okay. And the next problem we're going to look at is number 17. And then we'll have finished everything that I need to cover from this section. And this is section 3.1. So for number 17, we have the equation x equal 4. And we have the equation y equals negative 5. And that, again, they want us to find the intersection. Where do those 2 lines cross? Well, I guess first of all, it might be kind of nice if you knew what kind of lines those were. Yeah, one's vertical, one's horizontal. Which one is which? Now, if you don't know this, you might want to make a note of it. Kind of important to know to be a good human being. That if you have x and no y, that's vertical. Y and no x is horizontal. And then I'm going to solve this by using the graphing technique. So I'm going to graph the vertical line x equal 4. I'm going to graph the horizontal line y equals negative 5. And look at that. I can see where they intersect. Yeah, actually, yeah.
Oh.
Yeah, so if you're trying to find the point of intersection of a vertical line and a horizontal line, you shouldn't even need any technique. It's because it's basically telling you what x and y are. X is 4, y is negative 5. Is it always that easy?
No.
I mean, if they're vertical and horizontal.
Oh,
yeah. Yes. If they're special. Woohoo! Yay! And now I'm going to move on to page 163. Section 3.2 coming up next on page 163. And we're going to jump straight to problem number 3. And section 3.2, I guess I'll underline that there. That's where that starts. Bam. 2y plus x. X minus 3y. Oh, x equals 3y minus 3. And the instructions say, solve the system by the substitution method. They specify solve by substitution. And the first thing I'm going to say is, to hell with that. I'm going to go to Desmos because I love Desmos. So what is the equations? Did you write them down? Wait, 2y plus x and the other one? Oh, look at that. Bam. So the intersection? 4.2, 2.4, which shows me that if I was going to try to solve that graphically, I would probably not be able to get the right answer because I can't graph that accurately. Y'all understand what I'm saying? So solving by graphing it's limited in its ability to do stuff. You do. So if you just said, well, it's about 4.2, that's not good enough. No. It's time for somebody to take their medicine. All right, so what technique did they specify? Substitution. And substitution is easy if you have a letter by itself. Again, what I just said is important. Substitution is easy if you have a letter by itself. Here I can see that x equals 3y minus 3. And so I can substitute in the first equation for x. Okay, so this equation is going to become 2y plus 3y minus 3 equals 9. Does everybody see what just happened? My first equation was 2y plus x. But x got replaced with 3y minus 3. And then I can solve for y. Combine like terms. And I'm going to go ahead and move the minus 3 on the fly, which gives me a 12. Oh, yeah, it becomes plus on the other side. And divide both sides by 5. Y equals 12/5. You see, doing it algebraically, I get the improper fraction. What did I get with Desmos? I got a decimal. But you know what? I bet 12 divided by 5 is 2.4, right? Oh, I'm sorry. I was thinking x. That's a y, right? Okay. So that's going to be equal to 2.4 for the y. Oh, wait a second. I'm not done, am I? I got y. What do I need? And so what I'm going to do is I'm going to be specific about where I plug this back in this time. I'm going to take this and plug it back in right here because that's where I have x by itself. I'm looking for x. I'd like the equation that says x equal. And so then we're going to take this down here, and it's going to say x equal 3 times 12/5 minus 3. And then thank God for calculators. 3 times 12/5 minus 3 can be done easily electronically. As an improper fraction? What? As an improper fraction? 41 over 5? Oh, 21 over 5. So 21/5 and 12/5. And I'm going to double box that because that's really the answer. And I'm sure somebody is thinking, but on a test, would I accept the decimal? Y'all remember what I've said before? If it's a terminating decimal, I will accept it.
I got a question.
Go ahead.
I put 3 over 5 and I got 36 over 5.
Yeah,
Yeah, you have 21 over 5.
I know. It's because there's the minus 3. You didn't do the minus 3 part of that yet. Got it? Okay, good. Anybody have any questions? All right, let's move on then. How am I doing with space? Let's go to a new page. Add a page. Number 11. 2x minus 3. And y minus 2x. 1. And the instructions say the same thing. Solve using substitution. Does one of those equations have a letter by itself? Okay, so that means I'm going to be able to substitute for y. Since I know what y is equal to, I can replace y with 2x minus 3. And so this second equation is going to become 2x minus 3 minus 2x equals 1. Did y'all see that? The y got replaced with 2x minus 3. And then the rest of the equation copies down. And then I need to do what? Combine like terms. 2x minus 2x. Uh-oh. I got a bad feeling about this. My x's cancel. How can I solve for x if my x's are gone? I can't. Is this thing that's left over even a true statement? It's false, right? You know what that means? No solution. Which means this.
Which one do you want to test? The top one or
Either one of these are the same. I don't think undefined is the same as those. So
those two.
Yeah, either one is fine. And I'm sure y'all are thinking, well, I like the second one because it's less writing. Right? It's not that we're lazy, we're efficient. Okay? So, can you tell me what does that mean about the graph? No. I don't know. Well, actually, they're not vertical or horizontal because they both have x and y. Now, what does that tell me about the graph? Well, there are. There's 2 lines. Huh?
They don't intersect.
Who said that? Yeah. So what does that mean, though? Oh, that's what I'm looking for. Finally. Yeah, they don't intersect. And what kind of lines don't intersect? Parallel. So if you get 2 equations that have no solution, that means, hey, those are parallel. Y'all might want to make a note of that. That's good stuff. And then like a good little math teacher, I'm going to go to Desmos and I'm going to prove it. So what was the first equation? And the second equation? Oh, look at that. Can y'all see that? Isn't that cool? When you do all of this number and letter moving around stuff, and then you can say, oh, look, the picture verifies what I did. Yeah, man, that's awesome. That's almost as enjoyable as writing code, like lines and lines of code, and then you run the program and you see this beautiful picture or whatever, you know? Never mind. It's about as good a feeling. All right, I got one more. Number 15. And this will be the third time now that we're going to solve using substitution. Or is it the second?
Substitute the second.
Okay, like the third. Solve using substitution. Do I have a letter by itself? And again, that means that I can substitute for x in the first equation because I know what x equals to. And here we go. So that first equation is going to become 2 times 3y plus 2 minus 6y equals 4. And did y'all notice the 3y plus 2 has to go in parentheses? Because the 2 is being multiplied by x, which means multiplied by anything I put in place of x. And the next step, you got to distribute. 6y plus 4 minus 6y equals 4. Oh no! Did you see that? Oh, man, so what am I left with? 4, is that true or false? So that means it's not no solution because that's true. Now this means something else. This means there's infinite solutions. How can two lines intersect everywhere? How is that possible? Huh? Exactly.
So you would move that positive 4 over the equal sign?
You could.
Would it still be infinity?
Yes. You know why? If I move the 4 over, it would say 4 minus 4, which is? And this side would now be 0 because there's nothing over there. 0 equals 0. Still a true statement. Yeah. So if all of the letters disappear and the resulting statement is false, what does that mean? But if all the letters disappear and the resulting statement is true, yeah. And what is it? That means that these two lines, they're getting it on. They're laying on top of each other, okay? They're touching everywhere. Yeah. They sure are. All right, so the one thing I haven't talked about is the words that you need to know, okay? Remember I said a while ago, I said consistent or inconsistent, dependent or independent, right? So let's talk about those real quick. Lines are dependent if they lay on top of each other. If two lines are the same line, they're dependent. Otherwise, they are independent. So the parallel lines, they would be independent. And the infinite solutions would be dependent. Do y'all understand the difference between those two words now? If the lines touch more than once, if they're the same line, they're dependent. Otherwise, they're independent. Okay, now consistent or inconsistent. Inconsistent means they never touch. So parallel lines never touch, they're inconsistent. Otherwise, they're consistent. And at this point, I'm ready to move on to page 171. And we're going to move on to section 3.3. Page 171, 3.3, we're going to start with problem number 3. Yes, sir.
This is going to be like an addition method?
Yes. Good. So I guess if you break it down, 3.1 focuses on graphing, 3.2 focuses on substitution, and then this section, 3.3, is going to focus on the addition method. And if I haven't made it clear how to tell when to use which technique, I'm going to summarize that now, okay? And y'all heard me say this a few times in the last section. I said, if you have a letter by itself, substitution is best, right? If you have like x equal or y equal, substitution is best. Do I have a letter by itself here? No. So substitution is probably going to suck if I try it on this one. If I add these two equations together, will one of the letters cancel? And that's how you know the addition method is best. If you can add up and down and get one of the letters to cancel, the addition method is best. And so we're going to do that. 9x plus 2x, 5y minus 5y, 6 minus 17. 6 minus 17. Y'all see what I did? I just added up and down. And then it's going to be super easy to get x by itself. Divide both sides by 11. X is negative 1. Now, I know x. What do I need? I need y. And so we're going to take this x back up here, and you're going to have to choose which equation to plug into. Do you want to plug that negative 1 into the 9x or the 2x? Top or bottom? Oh, I heard some people say bottom. And then you said top. You know what? It's a personal preference. You can go top or bottom either way, okay? I'm going to go top. Here we go. So that means that this equation is going to become 9 times negative 1 plus 5y equals 6. But if you plugged it into the bottom equation, you'll get the same answer. 9 times negative 1. Okay, look out. Negative 9 coming over, though. Makes it a plus 9. Makes that a 15. And if I divide by 5, I get y is 3. And there's my point of intersection. Remember, you need to write that as an ordered pair. And I'm going to double box that because that's the answer. And would that be consistent or inconsistent? Consistent. Would that be dependent or independent? What? Independent. Dependent is if they lay on top of each other and touch everywhere. Okay, so these are it's independent because it touches only once, and it's consistent Because inconsistent means no solution. So consistent means at least one solution. And dependent goes with lines that are the same line. I guess that's the easiest way to remember that. Inconsistent only goes with parallel lines. Dependent only goes with infinite solution, same line. Okay? And now you know what I'm going to do to verify? Oh yeah, I love Desmos. All right, so what was my first equation? 9x plus 5y equals, and oh, look at that. Bam. Let me zoom in some. Bam. Y'all are not nearly as impressed as you should be. That's awesome. That you can just type those in and click. Yeah, you can't use, no, but you can use it on your homework and studying and stuff. And in the real world, you know, when you get out and start your actual life and you're allowed to use your cell phone with the Desmos app, yeah. All right, next problem. Number 9. And we've got 2x plus 3y equals 1. And 4x plus 6y equals 2. I feel kind of like Pharaoh today. Y'all remember the Bible story? I feel like I'm experiencing the great Exodus today. Was Moses outside? Let my people go? People are leaving. Okay. Again, the instructions say solve using addition. Well, I'm not seeing any of those letters that'll cancel. Okay? So that means I'm going to have to do a little bit of work. Which would be easier? To turn a 2 into -4 or to turn 3 into -6? Or are they equally easy? I think so too. Yeah, so I'm going to multiply the top equation by -2. And if you're wondering, can I do that? As long as I do it to both sides, that keeps it legal, right? Whatever I do to one side, I have to do the other. So I'm going to distribute -2 into that equation, and that's going to give me -4x minus 6y equals -2. And then I can do the addition method, because now the x's, and the y's are going to cancel. And so what does that leave on the left-hand side? No, what's that leave over here? Yeah, 0. Nothing, right? Oh, no. That side's also 0. Is that true or false? So what does that mean? And what does that mean about the graph? If I were to graph those two lines, what does that mean about the graph? Right, and so if I graph those, I will only see one line because they actually lay on top of each other. Y'all understand that? If I graph, I'm not going to see two different lines because they're the same line. I think I better prove that. All right, what was the first equation?
The original?
Yeah.
2x plus 3y.
And the second one?
4x plus 6y.
Now, do y'all see two lines? Watch this. I'm going to turn the second one off. Look at that. And back on, off, and on. Do y'all see that? Okay. Man, Desmos is nice to help check those. Is that consistent or inconsistent? And dependent because they touch everywhere. Dependent lines lay on top. And the way I remember that, you know, if two people lay on top of each other, they get a dependent. So if two lines lay on top of each other, they are dependent, okay? Yeah. Thanks for laughing, Tracy. I appreciate that. Next, number 11. All right, so it's time for me to say something that I've not said yet that's important. Are y'all listening? If on a test, if it says solve using the method of your choice, like if you get to choose addition or substitution, if all of the letters have numbers in front, substitution is bad. You do not want to use substitution if all the letters have numbers in front. You know why? Because if you're going to use substitution, you have to get one of the letters by itself. But if all of them have numbers in front, that means you're going to end up with the F word. Fractions. And you don't want to have to work with fractions, okay? So if all of the variables have coefficients, should you choose substitution? No. Bad choice. Well, I would choose addition. And the first thing I notice is that the letters are not even lining up this time. So I probably want to go ahead and line up the letters first. All right, so we're going to have 5x minus 9y equals 7. Negative 3x plus 7y equals negative 5. The first thing I want to do is I want to line up my like terms. And then I can start thinking about what do I need to do to get one of the letters to cancel. Well, I don't think it's going to be very easy to turn a 3 into a 5 or to turn a 7 into a 9. So this is going to require that I work on both equations. Would you prefer to get the x's or y's to cancel? X's. Okay, we'll do x's because Ariel spoke up first. So the easiest way to do this, if these are not nice like the 2 and the 4 were a while ago, these are not nice numbers, just take these two numbers. Are y'all watching? Take these two numbers and flip them and stick them out front. So the 3 here and the 5 here. Take the coefficients of x and flip them, not the reciprocal, not 1/5 and 1/3, but by flipping them, I mean take and multiply by the other one's coefficient. And did you notice that they're both positive out there? Okay, so what is positive 3 times 5? Positive 15, right? 5 times negative 3. And then 15 minus 15? Do you see why I want to keep these positive? Because the signs are already opposite. So now let's distribute. Okay, so what is that going to give me? 15x, 27y, 21. Negative 15x plus 35y negative 25. And so by working on both equations, and because Ariel wanted the x's to cancel, it is, I mean, it's up to you, yeah. Well, I could have got the y's to cancel too. And now we're ready to add up and down. 15x minus 15x, cancel. What about 35 minus 27? 8. And then what about negative 25 plus 21? Negative 4. Divide both sides by 8. And that'll reduce to negative half. Yuck. Do y'all see what I'm going to have to do next to solve for x? I'm going to have to plug in a half and work with it. Really? Do y'all see that? I'm going to have to plug in a fraction and have to work with fractions? I don't think so. I hate fractions bad enough that I'm not going to do that. I'm going to go back to here. Yeah. So I'm going to take my 5x minus 9y equals 7. Negative 3x plus 7y equals negative 5. And I'm going to get the y's to cancel this time. So let's take the 9 and the 7 and flip them and distribute. And it may be a little more work, but I hate fractions enough that I'm going to do it. Seven times 5. Okay, 35x, 63y, 49. Negative 27x, 63y, 5. Everybody follow me? Now, 35 minus 27. 8x. Y's cancel. 49 minus 45. Positive. Divide both sides by 8. X equals a half. And then I need to write that as an ordered pair, correct? So as an ordered pair, one half, negative one half. I'm going to double box that because I think it's the answer. And then I'm going to go to Desmos and I'm going to check it. And so what was the original first equation? Equals 7. And the other one? Negative 5? Oh, look at that. 0.5, negative 0.5. Is that a half, negative half? Wow, verified. Desmos is awesome. I love Desmos. And look at all that glorious work. Yeah. All right, I got one more to do, number 15. X minus 4y equals 5. 2x minus 4y equals 6. And again, it wants me to solve using the addition method. Are the x's ready to cancel? No. But what if one of those 2's was negative? Then it would cancel, wouldn't it? And so all I need to do this time is multiply one of the equations by -1, and that'll change the signs and get my x's to cancel. So we're going to multiply -1, and that's going to give me -2x plus 4y equals -5. And then I can add these two equations together. So my x's cancel. Uh-oh. Crap. And my y's canceled. And 6 minus 5 is 1. So what's on this other side? Nothing, right? Everything canceled? Is that true or false? And so what does that mean about the answer? What is it? So if I graph those two equations, they're going to be parallel. Yeah. Unless I made a mistake, right? No solution. They have no point of intersection. I could go back to Desmos and do that, but I'm actually tired of going back. So.
Are you going to still want the independent?
Oh yeah, let's do it real quick. Dependent or independent? And if I could reemphasize, the only way that you can write the answer as dependent is if the lines are the same line. That's the only way you can get a dependent, right? You got to lay on top of each other. And then consistent or inconsistent? Inconsistent. And if I could reemphasize, the only way that you can write the answer as inconsistent is if the lines are parallel. Inconsistent means parallel. Otherwise, it's going to be consistent. Got it? Yeah, I do want that. Thanks for asking for that. I appreciate it. And I'm going to go ahead and